Do you know, does anyone know who Bettina is? Yeah. Are you here to fix? I'm trying to type in the Zoom link because the speaker's running via Zoom. Oh, okay. Then I'll just continue. He sent me the link, so. It's wrong link or? Oh wait, we can actually go to Zoom. Does it say join a meeting anywhere?
C'est vraiment join a meeting.
Meeting ID 856 545 536.
Yes, no. Open Zoom. Okay. What is the no? Because this is what is the name of the?
You can put anything because like he's in there already.
Okay.
Password 022904. Yeah.
Okay. I don't know.
Hello.
Okay. So this is hi.
Hi there, can you hear me?
Yeah, we can hear you, but we don't see you.
Can you see the screen share?
No. Oh, yeah. Not sure.
I also have video.
Yeah. Okay. Okay, that's better. We can see you right now.
Great.
Okay. I think we can start? Okay, yeah. We can start when you want.
Cool. Well, it's a little tricky when I can't see the audience, so I'll just assume that there is an audience. Thanks for coming. Coming to you from coronavirus-proof remote Zoom. This is IBC and Ethereum 2.0. I'm Chris, and I work for Interchain GmbH. So to start off, I'm going to cover the agenda for this talk. First, I'll go over some of the hard problems, hopefully a pretty comprehensive list of all the hard problems in cross-shard and cross-chain communications. I think the hard problems in cross-shard communications and the hard problems in cross-chain communications are mostly the same. And I'll go over what those are and how they can be solved by sort of common solutions between ETH2, IBC, and a lot of different protocols. I'll give a quick introduction on top of IBC or in cooperation with IBC. And I'll talk specifically about what components constitute the IBC protocol and how they work to solve those problems. Then I'll give a quick overview of my limited understanding of the state of cross-shard communications planned for phase 2 of ETH2 at the moment. Talk about what problems seem to be receiving a lot of attention, what problems haven't yet received some attention, and where I think it might make sense to refocus a little bit. Then I'll analyze where IBC could help, ETH2 in particular, for the task of cross-shard communications and dealing with some of those sort of problems that I'll get to. And I'll talk about if IBC were to be integrated into the ETH2 roadmap, what approximately that would require, what it would look like, how it would compare or need to be integrated with some of the existing solutions which have been proposed, and what next steps would need to happen to realize that. Please, I don't know if there's a provision for questions. Maybe I'll just take questions at the end. That's probably easiest. Cool. So let's talk about hard problems and cross-shard chain communications. You'll notice that I've put cross-shard and cross-chain here in the same category. It's because I think the hard problems are mostly the same. The difference between shards and chains is simply a difference in authentication. In the case of multi-chain communications, you have chains with heterogeneous consensus algorithms which must authenticate each other. In the case of cross-shard and multi-shard communications, you have chains with independent execution, but where you have some a priori information about what their consensus is. Maybe you know what the validator set's going to be, maybe you know exactly what the shards are. So the difference is in authentication, but most of the other hard problems are the same. What are the hard problems? First is transport. You need to get data from one shard to another shard or one chain to another chain. You need to get it to the right place and you need to get it there within some reasonable time bound. The second is authentication. You need to ensure that when you're sending data from one chain or one shard to another chain or shard, it's the right data. You don't want someone to be able to send the wrong data and accept it by accident. That would be some kind of fraud. The third is ordering. In order to reason about the behavior, sort of composite behavior of applications which exist on multiple shards or multiple chains, you will need some or potentially many kinds of ordering guarantees provided by the communications mechanism that allow you to reason about what states are possible and what states are impossible. The fourth related concern is state dependence / atomicity. So in thinking about, from the high level as a user or an application developer who's developing an application that exists, that has state on multiple shards or multiple chains, you might need certain state transitions to be dependent on one another, or atomic. You might need to book a hotel and a train at the same time, either both or neither, right? That's sort of the classic case, but there are also cases that be dependent. You could only other things happen first, or perhaps you need some complex interoperation between multiple finance contracts, things like that. The fifth concern is denial of service resistance. You want to make sure that whatever your communications mechanism is, it can't be easily DOSed, because these are all public networks. The sixth concern, or sort of related point you have to think about when thinking about these other concerns, is the topology of your network, whether you have a fixed set of say shards where you know all the validators a priori, or whether that's changing, how that affects what you need to think about as you're architecting secure authentication in particular for your communication protocol, how that affects what you need to think about if you ever have to reroute messages from one place to another because the topology changed. And relatedly, the last hard problem on my list here is load balancing. This applies in particular to shard systems where you have some kind of uniform contract environment, but you want to balance the compute load or the storage load across different shards. And so you need to come up with a protocol for doing that, and probably one that is resistant to adversarial actors who want to foil it. So as you'll see, only really one of these problems, authentication, and to a somewhat lesser degree load balancing, is specific to sharded systems as opposed to specific to cross-shard systems as opposed to cross-chain systems. The authentication changes, but all of the other hard problems basically remain the same, whether you're dealing with homogeneous or heterogeneous consensus algorithms. So what's IBC, and which of these problems does it solve? IBC is a messaging protocol for the interchain. So it's basically solving the same set of problems, more or less, as the ETH phase 2 has to think about, as sharded contract system has to think about, but it's solving them in the context of heterogeneous chains with different consensus algorithms, different state machines, and a topology which is not known and which is changing constantly. So IBC addresses some of these problems, and it purposefully does not address others of these problems because we think that they should be addressed at a higher layer on top of this base protocol. Which problems does it address? IBC solves transport, getting data from one place to another. It solves authentication, ensuring that the data that you're receiving on one chain, say in one module or contract, is in fact the data that was sent by another module on another chain. It solves ordering, ensuring that if you want ordering dependence between packets of data that you're sending around, you get it. It can handle completely dynamic topologies where you don't know the set of chains or set of shards a priori, and it can change even when you have messages in flight. It can be changing all the time. And it deals, of course, with heterogeneous chains that consensus algorithms. IBC does not solve, at least natively, it does not solve denial of service resistance, so we have some sort of gap limitation mechanism on the chains onto which you're running it. IBC does not solve state dependence atomicity at the core protocol layer. Instead, you have to build that on top. I guess you can rely on the ordering properties, but then you have to reason about what sort of composite state guarantees you need to provide and construct your application accordingly, or build something like a lock protocol on top of IBC, which I'll talk about in a second. IBC does not solve load balancing. You would do that on top, and IBC in particular, which may be relevant to its compatibility with ETH2, does not currently deal with forks or rollbacks. It assumes that verification of consensus of shards or chains can be performed in a final sense, that the other shards or chains commit to a final result and it won't change. Two quick myths that I wanted to debunk. IBC is not Cosmos specific. The Cosmos Hub blockchain plays no necessary or central role. The word hub and the word zone, as you might have heard in our media, just refer to expected sort of roles within the topology that particular chains will play. There's no sort of permissioning system. You can use IBC without connecting to the hub. And the second myth is that IBC is not just about token transfers. In fact, the core IBC protocol, IBC TAO, is not about token transfers at all. It is constructed in a payload agnostic fashion, which I will get to right now. So the first part of IBC we call jokingly the tau of IBC for transport, authentication, and ordering. What does this consist of? IBC is written as a layered protocol stack. You can think of this as pretty similar or analogous to the OSI model in TCP/IP, where different layers sit one on top of each other. Each provides an interface to the next layer. Each provides a set of security guarantees, and the layers themselves can be instantiated in different ways. So just as different layers of the TCP/IP protocol can be instantiated sometimes in hardware, sometimes in software by physical and virtual devices, and they just have to remain protocol compliant. As long as the devices remain protocol compliant, you can build HTTP websites, etc., further protocols on top of it, even though the implementations of the primitives vary. IBC works exactly like this. There are a set of primitives, a set of abstractions, which have certain properties and which you can use to, which you can combine together to get the high-level messaging, authentication, transport, ordering properties you want, but then those primitives can be instantiated in different ways. So the key primitives in the tau of IBC are clients, connections, channels, packets, and modules. Clients serve to allow you to verify consensus transcripts. So in the case of a multi-chain system, clients will allow you to check. It's basically a light client. Clients will allow you to check that the consensus algorithm of another chain committed to a particular state, which you can use then to verify the components of that state, such as outgoing messages. In the case of a sharded system, clients would potentially be proxies. You might be using the, let's call different things. In Polkadot, it's called the relay chain. In Ethereum 2.0, it's called the beacon chain. But you might be using a central chain as a proxy to verify the state on other shards. But it works basically the same way. Connections serve to associate two chains or two shards, allow them to refer to each other in a way that prevents the man-in-the-middle attacks, any sort of forgery. Channels serve as a data pipe between two modules. So IBC uses the sort of agnostic term modules. A module is just an independent unit of code execution. It could be a smart contract. It could be a module in a state machine framework, such as the Cosmos SDK or Substrate. But critically, modules are isolated from each other and they may not trust each other. So IBC allows modules to create secure data channels to other modules. Just as you might be writing an Ethereum contract and not want to worry about whether the other contracts on the Ethereum chain were correct or not in order to reason about the correctness of your contract, you don't want to worry about whether the other contracts on some other chain, apart from the one which you specifically want to talk to, are correct. And IBC lets you do that. Packets are where, of course, all the actual action is at. So all of these lower abstractions are payload agnostic. They don't specify what actual data is being sent around or what it means. They don't specify the semantics of it. That's all contained in the data packet. And the data packet can be routed between these modules, only the endpoints, only the modules at the end of the channel at each end of the channel need to understand how to interpret that data, how to create packets, how to parse packets, and treat them accordingly. Then the final element here, which we're touching upon, is relayers. Relayers in IBC are simply off-chain processes that are responsible for physically transporting data from one place to another. So this can coincide with validators. Validators who are running these networks obviously are running the shards, or running the chains, have access to the data, so they can serve as relayers, but it doesn't necessarily need to coincide, so we separate it as a role. So as a quick physical layout of what this all looks like, step by step, you start out on module A on the left, number one. Module A sends an IBC packet that gets routed through the IBC module running on chain A. It then gets committed to in the consensus algorithm of chain A, or say included, if this were a shard instead of a chain, it would be included in the next block of the shard. Then a relayer picks it up, sends it over to chain B or shard B. It gets routed to the appropriate module, module B, and module B can handle it as necessary. If module B succeeds, module B might send back an acknowledgement of success, or if it fails, it might send back a notice of failure with the appropriate error code so that module A can take action to revert state changes or whatever. And then there can be ordering guarantees imposed on top of this if you want order between packets, such that the first, the packets will be received in the order in which you sent, or if you don't care about the order, or if you want some more complicated direct acyclic graph, all of these things are possible. So on top of the core protocol sits the application layer packet semantics. Application layer packet semantics in IBC are a lot like ERC or EIP standards in Ethereum, which talk about specific kinds of cross-contract calls. Except in the case of IBC, we're talking about calls between different modules, essentially on different chains, written even in different languages, or they could be smart contracts. But the basic idea and the basic concept is the same. Each packet contains some serialized data. That serialized data has a particular format, and that format can be interpreted in an appropriate fashion by the sending and receiving ends to do something. You might use packets to send token transfers. You might use packets to delegate control of an account on one chain, or a smart contract on one shard to another chain, or another contract on another shard. You might use packets in something that's similar to contract yanking, one of the ETH2 proposals, which I'll talk about in a second, to do interchain code relocation, where you transport contracts between state machines with compatible VMs or execution environments. Let's talk about briefly then what the current state of cross-shard communications is in ETH2. Based on my sort of survey of the research landscape, so far there's been a lot of reasoning about atomicity, the train hotel problem, or the composable DeFi problem. There have been proposals for sequential receipts, contract yanking, moving contracts around to get atomicity, merge blocks, where you sort of impose some requirements on the shard consensus in order to have combined blocks every so often where you can execute atomic transactions, optimistic state roots or optimistic concurrency, read-write, basically mutual exclusion locks, which is something similar to sort of multi-version concurrency control, or sharded Byzantine atomic commit, which is a protocol specifically for like fault-tolerant blocking. There has been, as far as I can tell, not too much reasoning so far about dynamic topologies. I actually don't know what the exact number of shards currently proposed for ETH2 is, but it seems to be a fixed number, maybe one that would change later, but not one that would change day to day. There doesn't seem to be too much reasoning yet about how to deal with specialized execution environments that might not support the same sort of contract VMs. And there doesn't seem to be too much reasoning yet about application-specific concurrency techniques. Of course, sometimes you really just need locks, but locks are quite expensive in a cross-chain context or cross-shard context. They require a bunch of transactions. You have to reason about DAS concerns, et cetera. So I think that some approaches from the academic literature, like conflict resolvable data types, CRDTs, or lattice variables, which use a sort of lattice-based concurrency technique, since they require either don't require locking or require more limited locking, might be applicable here. So if IBC were to be integrated into the ETH2 specification process, where would it fit? IBC is a protocol layer that would sit between shards in the beacon chain and contracts or higher level concurrency protocols. So the sort of application layer of IBC is basically equivalent to cross-chain contract calls in ETH2, and the tau of IBC, the transport authentication and ordering layer, would sit between those cross-chain contract calls and sort of the core state machines. IBC is compatible with most of these existing proposals if it were to be fitted. Sequential receipts are basically the same thing as ordered IBC channels, so you already have that built into the protocol. Contract yanking would sit on top of IBC as an application layer protocol. Merge blocks are not yet possible because they actually affect sort of the consensus rules of shards, and IBC is not written that way, although it would be possible to alter it to work that way, potentially. Optimistic state roots and optimistic concurrency kind of depends on the mechanism, but some form of that should be possible. Read-write mutual exclusion locks are possible over IBC, they're an application layer protocol, and sharded Byzantine atomic commit is possible on top of IBC. It's even possible across heterogeneous chains. It's kind of like running a BFT algorithm on top of BFT chains in a sort of fractal sense. So if we were to integrate IBC into the ETH2 roadmap, what would this look like? And what are the pros, cons, and next steps? Pros of integrating IBC, whether you call it IBC or not is not the most important question. It's more about whether you construct this kind of layered protocol stack and whether it's instead of, one way the ETH2 spec process could go for phase 2 is that there's sort of one cathedral concurrency solution that's built into the core protocol and everything kind of has to use it. Maybe it has some fancy features like merge blocks. That's one approach and it has some advantages. IBC is not that approach. IBC is a much more layered approach. So if you were to integrate IBC, it would be more like you build these layers and they support more and more advanced sorts of concurrency or atomicity primitives and reasoning. And then depending on what your application needs, you can interface with the cross-chain communications facilities provided by ETH2 at a different layer. You might just need asynchronous message sending, you might need some sort of ordering, you might need something more complex to get atomicity. Those requirements will really vary based on the application. So I think there's something to be said for allowing applications to interface with your system at different levels. So IBC provides, in that sense, quite a few advantages. It's a clear set of abstractions, it separates concerns. Because of the way IBC is written, it's very easy to deal with topology changes because IBC doesn't make any assumptions about topology in the first place. So if the number of shards changes, even dynamically, IBC can handle that. It's easy to reason about directly in applications. Developers who are familiar with channels or other concurrency primitives in Go or Erlang or something will be familiar with the interfaces which IBC exposes. It's easy to build higher level protocols like sharded Byzantine commit on top of IBC. And it would also provide a natural unified interface to non-ETH 2.0 chains for contracts. So that contracts kind of handle talking to other contracts on ETH2 and talking to other modules on other chains in the same fashion. Maybe another chain in this case could even be ETH 1.x. Cons, IBC would require alteration as it stands to handle some of these concurrency or cross-chain, cross-shard mechanisms that require altering consensus rules. At the moment, IBC doesn't do that. And it would also require alteration to handle rollbacks or non-finality. At the moment, it assumes finality. Both of these alterations are possible, but they would be substantial, so it would be worth figuring out exactly what that would mean and if ETH2 really wants to integrate those into its cross-shard communications mechanism or not. Finally, what would be the next steps? So far, I think, of course, most of us are operating in silos here. I lead specification of IBC and alongside a lot of other fantastic contributors, notably Gorak, Informal Systems, All Bits, Interchain GmbH. And I know there are lots of fantastic scientists and researchers working on ETH2 specs. If we were to try to integrate things in this fashion, I think it would require some intensive discussion and collaboration, perhaps on the ETH research forums. I think we're pretty flexible between the IBC team and the ETH 2.0 spec team to figure out where IBC would fit, what parts would fit, what parts would need to be changed, and if it all makes sense. So if that sounded interesting, and if you want to learn more, get in touch or talk about what we would need to do to actually integrate IBC into the ETH2 map, you can find the current specification, which is basically finalized, at least for the version that we'll be deploying on Cosmos, at github.com/cosmos/ICS. And you can find me on Twitter at twitter.com/CWGOES. Thank you.
Thank you. Unfortunately, we don't have time for questions, but you have his Twitters. Oh, sorry, I was not speaking. Unfortunately, we don't have time for Q&A, but you have his Twitters. And thanks for being here with us on Zoom. And please reach out to him if you have any question. And thanks for your work on Ethereum too.
Thanks, everyone. Ciao.